of the aluminum. So this is equal to 23 times 10 to the power minus 6 multiply by change in temperature 140 minus 20, right? So T1 is your new temperature. Your reference temperature is T0. Okay. And then the coefficient, sorry, the length is equal to 0.3. So this will be equal to 828 times 10 to the power 6 meters. So this is for the aluminum. We allowed it to expand. Okay. And then the next one, we're going to look at the stainless steel. So this is the easy part. Okay. So this will be equal to, so the coefficient of thermal expansion is 17.3 times 10 to the power minus 6. The change in temperature 140 minus 20. And then the length for this case is 0.25. I do apologize. All these are plus. Okay. Now, plus means what? It's going to be in tension. I mean, it's going to elongate, right? Okay. So this will be equal to plus 519 times 10 to the power minus 6 meters. Okay. So we're going to have the total deflection due to temperature. So it's 828 times 10 to the power minus 6. Okay. Plus by 519 times 10 to the power minus 6. Okay. So this will be equal to 1.347 times 10 to the power minus 3 meters. Okay. Right. So the actual deflection. So what does this mean? Okay, what does this mean? Right. So I'm going to draw a graph to explain. Okay. So we have. Yeah, I never thought about using graph to explain, and I think that's a good idea. So now we have our okay. So this is 0. Then we will have, wait, this will be 1, 2, 3, 4, 5. 0.5. Okay, times 10 to the power minus 3. 1, 2, 3, 4, 5. 1.0. And then you will have okay, 1, 2, 3, 4. So this is 1.5. So this is your deflection due to temperature. And then on our y-axis is our stress. Okay, our stress over there, I don't know what stress is it. I only know have stress or no stress. Okay. So this is my y-axis. Okay. Right. So then we will have, so we know that it will stop at 140 degrees C is going to be 1.347. So 1.1, 1.2, 1.3, 1. So I'm going to eyeball this. Okay, so this is our 1.347 times 10 to the power minus 3 meters. So the units down here is times 10 to the power minus 3 meters. Okay, so I can just put in 1.347. So what does this mean? Okay, so because of our gap, okay, so this is the stress. Okay, the stress can be steel or aluminum, either one. Okay, I don't know. Okay, I'm looking at it as a global. Global means the entire structure, right? So if it's time based, right? So this were okay. So this will be at 0 initially. Yes or no? So I heat up the thing. The gap will start to reduce, and the structure will start to get longer. Yes or no? At 0.5, what will happen? Right? At 0.5, then you will see a build-up in stress. And then it will do this. Okay? It will do this. Right? So what I'm trying to say down here is this. The amount of deflection induced by heat that will induce stress is only this amount. Right? So from here to here, right? From here to here, from here to here, then you see stress induced by temperature change. Right? Does that make sense now? So the distance from here to here, the distance from here to here will be equal to 1.347 minus by the gap 0.5, and this will be equal to 0.847 times 10 to the power minus 3 meters. Does that make sense to all of you? Yes or no? Right? Initially, we have a gap. So when there's a gap, no one is touching at all. Then all of a sudden, when the gap goes 0, then the structure will see a stress. Okay? Are we clear? Earth calling Mars. Are we okay? Right? Okay, so the actual... Any questions so far? So you guys are clear? Okay. So the actual deflection...
Sir, why did you pick 0.5?
Because of the gap.
Oh, the gap is 0.5. Okay.
Okay, because of the gap. Okay.
All right. I forgot that. Sorry.
Yeah, it's okay. It's okay. Okay. So what we realize now is that the actual deflection actual deflection which induced thermal stress is equal to 1.347 times 10 to the power minus 3 minus 0.5 times 10 to the power minus 3. So this will be equal to 0.847 times 10 to the power minus 3 meters. Okay. So next is this. Okay. We have to see what will happen when gap is equal to 0. Okay. When gap is equal to 0. Okay, we have to see what will happen when gap equal to 0, right? So we know that when gap equal to 0, it's going to touch, but what's going to happen to the structure now? So I'm going to copy this structure. All right. So we know that on the left-hand side, we have our aluminum. On the right-hand side, we have our stainless steel, or we have our steel, right? I'm going to use different color because I'm going to explain this on color. So this is our aluminum. This is our steel. So now, I'm going to induce this where the gap is equal to 0 now. Okay. So when the gap is equal to 0 now, okay, watch what is going to happen. There's a force acting on the aluminum. Okay. And it's going to induce a what? Compression on the aluminum. Okay. And then on the other side, there's a force that's going to be induced on the steel. Okay. Because now your gap is equal to 0 already. Right? So what you can see over here, when gap is equal to 0, this is the force that is going to happen. And we're going to base it on Newton's third law. Anyone can tell me what is Newton's third law, please? Anyone? Give me another, the way I look at it, give me another like 10 minutes. We'll be done maximum. We're almost done. Okay, we have passed the most. So what's Newton's third law?
Action and opposite reaction.
Well done. So Newton's third law is action. Whenever there's an action, okay, action equals to reaction. Same in magnitude. However, opposite in direction. So to make it simple to remember, I punch you, you punch me. Okay, same force but different direction because you don't punch yourself. Yes or no? Right. So from here, we realize that the force acting on the steel is going to be compression. On the steel, that's why it's minus, is equal to the force acting on the aluminum that's also in compression. And based on Newton's third law, both of them are the same, and we can call it what? We can call them equal to minus P. Okay, we can call them to minus P, right? So the next part of our problem now is we have to calculate how this force or what we call our redundant force are acting on our structure. So where we are now in our solution procedure is we are here now. Okay, we are here now. Right? We are here now. We have to use the equation to relate to the mechanical loading that's pushing when gap is equal to what? When gap is equal to 0, when there is no gap, there's going to be what? Reaction. Okay, so now we are looking at the reaction due to mechanical loading. Okay, because temperature is already expanded, they have nowhere to go. Now the forces, the mechanical loading, okay, the load acting on the stainless steel and the load acting on the aluminum is going to induce stresses. Okay, so now we're going to apply. Oh, end of page. Okay, I'm going to copy this structure. And we're going to go here. Okay, so what you see now is we're going to apply that. Okay, this is due to the load is PL over what? AE. Okay, so delta P is equal to P of aluminum, L of aluminum divided by A of aluminum, E of aluminum, plus by P of steel, L of steel, A of steel, E of steel. Okay, so this will be equal to, so we know that the P for the aluminum, the P of the steel is all equal to what? Minus P. Now, why minus? Because the load, the P of the aluminum is going to induce compression. That's why minus. The P inducing on the stainless steel is also in compression. That's why both of them are minus. Okay, so you just put minus P times by 0.3, which is the length. And the cross-sectional area is what? The cross-sectional area is 2000